Hello students, welcome to this module on mathematical preliminaries that are required for the course Introduction to Hydrodynamic Stability, CHE 614 taught at IIT Kanpur. So what I'm going to do in this module and probably the next couple of modules is to introduce you or refresh your minds regarding the rudiments of elementary basic linear algebra and function spaces. You may be wondering why we are actually doing linear algebra after or linear problems after discussing nonlinear dynamics. The idea is that one of the primary tools to understand the onset of transition in fluid flows is linear stability analysis. I had introduced you to the notion of linear stability analysis in the context of simple ordinary differential equations. Suppose I have dx dt is a nonlinear function f of x, and if f of x star is 0, this gives you one or more, of course if it's nonlinear it will give more fixed points, x star, a number of fixed points. And if you are interested in understanding the stability of the fixed point, what you do is you say x is equal to x star plus some deviation from x star, right, by dt is equal to f of x star plus eta. Now dx star by dt is 0 by definition because it's a fixed point. Okay, so what therefore we'll do is we'll say that the left side is simply d eta dt is equal to, this is f of x star, which is 0, I Taylor expand the right side, times df dx evaluated at x star times eta plus higher order terms, quadratic and other higher order terms. The key idea is that because we are interested in eta small, the magnitude of eta is very small, these are negligible. Such an analysis is called a linear stability analysis. Okay, the reason is that you are interested in only retaining the term that is linear in the perturbations, and you are not going to worry about these higher order terms in the context of predicting the onset of the instability. Okay, so therefore while this is in the context of ODEs, okay, what the Navier-Stokes equations are, they are PDEs, partial differential equations. So we need the mathematical preliminaries to do a linear stability analysis of Navier-Stokes equations. Many of you might already have this background in mathematical preliminaries, but since it's a diverse class and many of you may not have taken the previous course which I taught, which is CHE 641 on mathematical methods, I thought I will spend a couple of modules to just refresh your minds and introduce you briefly to the ideas that are essential to doing or carrying out a linear stability analysis of fluid mechanical problems, such as fluid flow as described by Navier-Stokes equations. Now, so let's start with the notion of a function. You can think of functions as generalized vectors. Okay, a vector is an ordered array of numbers, right? Some a1, a2. So I'll call this a vector A, which is given by these components in a given basis. I'll tell what we mean by basis in a moment. It's basically a coordinate system, for example, that you choose. Functions can be thought of as generalized vectors in an infinite dimensional space. The simplest way to think about it is that suppose I have a function in a domain 0 less than x less than or equal to 1 or something. So you have the domain 0 to 1. Okay, typically whenever you want to tabulate the function or solve for the function from a numerical method or something, differentiate or integrate the function numerically, you will try to chop the function into chop the domain into intervals. Okay, and then you will represent the value of the functions at these points. If I chop the domain into n points, then the function will live in an n-dimensional space. Okay, but in reality you have infinite dimensions because you can pick the point arbitrarily close to each other, and there is an infinity of points. That means that a function actually can be thought of as a generalized vector in an infinite dimensional space. Okay, now if you have a vector in a finite dimensional space A, then in general you can have an operation which operates on A to give rise to another vector B. Okay, and this operation can be a linear operation wherein if I take M and then alpha A plus beta B, where alpha and beta are scalar numbers whereas A and B are vectors, then this will be given by M A alpha times M A plus beta times M B. This is the definition of linear operation. Okay, now similar to, so if I take a vector A and then I operate it with an operator, let's say it's a linear operator as defined by this, then in general the output will be another vector, a different vector B. Okay, in a similar fashion you can have operations on functions. For example, you can have d squared by dx squared operating on a function to give rise to another function. Okay, or you can integrate a function and to give rise to another function. So these are all operations on functions, very similar to operations on vectors, finite dimensional vectors. Okay, so we will go back and forth between finite dimensional vectors and functions, which can be thought of as the limit of an infinite dimensional vector. Okay, so let's first talk about the simplest case where you have a two-dimensional space. Okay, you have two orthogonal unit vectors. Think of this as the geometric plane, xy plane, let's say, and the two vectors are orthogonal, and any vector A in this plane, xy plane, this is A, can be expressed in terms of its components along the two coordinate directions. Okay, so I will call this A1 and I will call this A2. Okay, then from simple law of vector addition, you know how to find the resultant vector A in terms of its components. I'm sorry, I'm using AX and AY, so let me be consistent here. Okay, so these I1 and I2 they are called variously as they are unit orthogonal vectors in a plane, in the plane, and they are called basis vectors. Okay, so any vector in the plane can be expressed in terms of such a combination. You can take another vector B, you can write it as bxi1 plus byi2. Okay, any vector in the plane can be represented in terms of these basis vectors. Okay, so we say that I1 and I2 form a basis in the plane because any vector on the plane can be expressed using I1 and I2 as basis. Okay, so we can think of I1 as the vector 1 0 and I2 as the vector 0 1. Then A is the column vector AX AY is nothing but the coefficient AX times 1 0 plus AY times 0 1. Okay, if you know elementary matrix multiplication, you know how to do this, and you will find that A is AX AY, or you can think of it this in terms as AX I1 plus AY I2, because this is I1 and this is I2. Okay, now you can also think of AX and AY as the components of A along the I1 and I2 direction. Okay, or you can think of AX and AY as the projections of A along I1 and I2. These are all just jargons that you should get used to. Okay, so how do you find AX? AX is nothing but A dot I1, because if you take A dot I1, this is A dot I1 is AX I1 plus AY I2 dot I1. Okay, this is nothing but AX times I1 dot I1 plus AY times I2 dot I1. Now this is 0 because I2 dot I1 is I1 and I2 are perpendicular to each other. That's the assumption we have made. And if I assume that I1 dot I1 is a unit vector, this is 1. So that's why you get AX is equal to AX on both sides. Okay, right. So one thing that you should note is that this basis comprising I1 and I2 is not anything special. Okay, you can have equally another set of bases E1 and E2. Just to think concretely, you can think that you may think that E1 and E2 are just simply obtained by rotating about I1 and I2, like shown here. Okay, now these are, again, I'm going to assume these two to be orthogonal. That is, this angle between E1 and E2 is 90 degrees again. So I can write the same vector A. Note that I have this vector A now in terms of E1 and E2. So I can write A as A1 E1 plus A2 E2. Note that the coefficients A1 and A2 are in general not equal to AX and AY, because they are now the coefficients of this same vector A, but expressed in a different basis, okay, which is now the E1 E2 basis. Now we know that, but what is the relation between AX AY and A1 A2? This is what we'll try and show very easily now. AX is nothing but I1 dot A. We just saw this here. AX is A dot I1 or I1 dot A. Okay, but this is nothing but I1 dot, instead of A, I'm going to write this expression, a1 expression here. So instead of a, I'm going to substitute this expression. So this is, instead of a, I'm going to put a1 e1 plus a2 e2. This is ax. This is nothing but a1 I1 dot e1 plus a2 I1 dot e2. So ax is now represented in terms of the components in the original basis, which are a1 and a2, but now it involves the projections of the basis vector I1 along the coordinate directions e1 and e2. Okay. Similarly, you can write another expression for ay, which I will not do here. Okay. So the key idea is that you can switch from one basis to another. And things are simpler if the basis is orthogonal, like the ones we have assumed. Okay, otherwise you will have to do a little bit more algebra. Okay, now the fact that you have an orthogonal basis allows us to find out all these coefficients in a simpler manner, because if you want to find what is ax, it is simply I1 dot a, and there is no worry about I2 here, right? So that is the advantage of an orthogonal basis. Okay, now let's think about a linear transformation. Suppose I have m, this is a linear operator as defined a few minutes before the beginning of the module. Let's say m operates on a to give rise to another vector b. Many a times you will find that there are two types of things that you can worry about in such problems. First is a is given, find b. Second is b is given, find a. Okay, now let's think about how we go about doing the second one. Okay, so we have m dot a is b. Let's choose a given basis. Okay, now now I want to express or I want to take this is a vector equation. I want to now express find the I1th component, so I have to dot it with I1. Okay, so I1 dot, instead of a, I'm going to write its components ax I1 plus ay I2 is equal to I1 dot okay. Now because it's a linear operator, this operator can go in, so I will get ax is just a number, ax times I1 dot m dot I1 plus ay times I1 dot m dot I2 is equal to, now I1 dot I1 is 1 if I have defined my basis in an orthonormal manner, so this is simply bx, and I1 dot I2 is I1 dot I1 is 1, I1 dot I2 is 0. Now similarly I can have another expression if I dot it with I2. Okay, so the next thing that I can do is I'll say ax times I2 dot m dot I1 plus ay times I2 dot m dot I2 is nothing but b dot I2, which is by. So you have two expressions. Now I'm going to call these objects as M11, M12, M21, M22. Okay, so once I do that, I'll get AX M11 plus AY M12 is BX, and AX M21 plus AY M22 is BY. So these are two sets of coupled linear equations. Okay, they are coupled because you cannot solve them separately. The equation for both the equations have both x and y, ax and ay. Okay, now think about a case like this. If I were to have a hypothetical case okay, let's put a prime here. These are uncoupled because I can simply write ax prime as bx prime by M11, and you can solve these two equations separately. Ay prime is by prime upon M22. Now I want to solve this equation also in as simpler a manner as the uncoupled equations. So the key idea is that coupling is avoided if the cross terms in this equation, if these are 0, then you will avoid coupling. Coupling is avoided if M12 and M21 are 0. Okay, so what we are trying to say is that if I operate the operator M on I1, it should not give any I2. The resulting answer should not have any I2. It should be purely pointing in the direction of I1. So let me write this properly. M dot I1. Similarly, M dot I2 should be proportional to I2. That's the only way where I will guess. Okay, so let's call this special basis. Let's not use I1 and I2, that is the older basis. Let's call this special basis where M dot E1 is 1 is in superscript, so let's just keep that, is E1, and M dot E2 is proportional to E2, right? So this is the first criterion. The second criterion is that EI dot EJ should be delta IJ. These are orthonormal. Okay, these are the two conditions which will simplify the solution of this set of coupled equations. Okay, now how do we do this? So we want, let's change the proportionality to an equality. So we'll say M dot E1 is some constant lambda 1 E1, and M dot E2 is some constant lambda 2 E2. If such is the case, then you will not have any off diagonal coupling terms. Okay, now if you look at this set of equations, you will realize that this is just the eigenvalue problem for M. Therefore, if we solve the eigenvalue problem for M, okay, and E1 and E2 are eigenvectors of M, while lambda 1 and lambda 2 are the corresponding eigenvalues of M. Okay. Now this orthonormal eigenvectors are guaranteed if M is Hermitian, or the more simpler cases if M is a symmetric matrix, okay, or a Hermitian operator. Alright, so let's assume that we have found or solved the eigenvalue problem of the operator M. Okay, therefore I am going to now, so the goal, if you wish, is to solve M dot A is equal to B, and we are interested in finding A, the vector A. Now to do this, let's assume that we are going to expand the vector A in terms of the eigenbasis of M. These are nothing but the eigenvectors of M. Okay, therefore I'm going to substitute this, so I'll say M dot A1, sorry, A1 is a scalar, A1 M dot E1 plus A2 M dot E2 is equal to B. But M dot E1 is lambda 1 E1, so you will get A1 lambda 1 E1 plus A2 lambda 2 E2 is equal to B. Okay, now because E1 and E2 are orthogonal, we have assumed them to be orthogonal vectors. Therefore, if I dot everything with E1 and they are orthonormal to be, let's say, EI dot EJ is delta IJ, then if I dot the entire equation with E1, I'll get A1 lambda 1, E1 dot E1 is 1, so this is B dot E1, that's nothing but B1, and similarly A2 lambda 2 is B2 from the second equation by dotting it with the other eigenvector, okay, E2, right? So from here what we can conclude is that A1 lambda 1 is B1. This means that A1 is B1 by lambda 1 and A2 is B2 by lambda 2. So the problem is solved because it's completely decoupled when you express the vector A in the eigenbasis of the operator M. Okay. Now this is a very, very important idea and a useful notion to have, because the same thing will carry over not just in the case of discrete vectors, but it will also carry over in the case of functions. So we'll stop here in this module and we'll start with functions in the next module. Thank you.